and also for inviting me to come here today to talk about some of the research that I started with John Castor, which in fact continued for several decades, and then segue into work that I have done in the last decade and a half, devoting my energies to, that have been inspired by the original work with John. So I want to start with the last few months of my doctoral thesis, which were done both at Brandeis University and Harvard University at the Center for Astrophysics. And during that period of time, in the last few months, John had offered me a postdoc to come to Boulder and work with him on setting the foundational theory of stellar winds. That was at the time and still remains an extremely hot topic in theoretical astrophysics. But prior to my actually meeting John for the first time, and I had accepted the offer, a postdoc came by Harvard named John Leibacher, who I got a chance to talk to. He was on his way to his next postdoc, and I was intensely interested in what life at JILA was like, and in particular, what working with John Castor would be like. And John Leibacher proceeded to give me the sagest advice that anybody has ever given me in having a deep collaboration with John Castor. He said very simply to me, John knows everything. And in fact, John can produce astounding work. So when you work with John, avoid becoming depressed, because you can easily become depressed, and avoid competing with John, because that's going to take you down a rabbit hole. Just go straight ahead, enjoy what John can do, work with him, and I must say that has led to not only a great friendship over these decades, but also in many fields with John, several papers, and a great collaboration. Okay, so when I then arrived a few months later to work with John and his then graduate student David Abbott, it was nothing less than developing the foundational theory of stellar winds, an extremely hot topic at the time. John's first research assignment to me, was to develop a solution for the singular point in the stellar wind. Now, the singular point is a very important point in the flow. It has to be determined because that's where you can have a continuous solution of a stellar wind and give some of the fundamental properties, and that's the launch point for developing the differential equations that one has to actually integrate. I've never done a singular point analysis at that point, so I spent the next 2.5 weeks spending a great effort producing about 30 pages of very dense algebra, and came to a conclusion that I thought I had actually solved the singular point problem. Sat down with John to show him what I had done. John took my 30 pages of algebra and he leafed through them the way you would leaf through cards in a deck. In about 40 minutes, he got to the end and he looked up and he said, well, Richard, this looks good, and I think it's right. But I think there's a more direct way to actually do this. So without taking any of the pages that I had developed over those intense 2.5 weeks, John went to the blackboard and covered right out of his head 3 pages of detailed approach, an alternative approach. And at the end of those 45 minutes at that blackboard, he arrived at the same result that I took 2.5 weeks and 30 pages of algebra. So that was the first miracle. And I was astounded. But then, and I got depressed. But then the sage advice of John Leibacher kicked in, and I said, no, you're not going to go there. You're going to move straight ahead. This guy is capable of miracles. Just accept that and enjoy yourself. So that was the start of a wonderful friendship and a fantastic collaboration over the next many years. Now, the first paper we wrote, which has become known in the world as the CAK theory, Castor, Abbott, Klein, has had a remarkable run. In fact, it's still running. As of this last week, it has already had almost 1,500 citations in the world literature all over the world. But what's really remarkable about the paper is, in fact, the fact that the paper itself continues to produce more citations every year. It's an upward slope. That's extremely unusual for any paper in any of the scientific fields. So it continues to make a major impact. Now, we had several major conclusions that came out of the original work. that were subsequently improved upon. The first was that the force on the stellar material produced by radiation absorbed in a large number of subordinate lines can be very large, and in fact lead to an expanding atmosphere that is a function, in fact, of the local velocity gradients. Okay, this resulted in a very large mass loss rate, some 2 orders of magnitude beyond what people had imagined. David Abbott, the great student of John Castor's, had finished his doctorate a few years after that, improved upon what we had done, and especially in the force calculation by bringing in essentially the ion group elements to the calculation, and he also looked at alternative ways to what we had developed as a treatment of line overlap. So we had developed a new stellar wind theory based on an analytic approximation to the force law. Now, John had done a lot of thinking about this before I even arrived in Boulder, and we were able to then attempt to attack the force problem by, we couldn't do the full non-LT problem of all the lines because there was no computational resource at that time that could do that problem. So John had realized that we might be able to actually get an analytic formulation of the force law, and this was key because I then used that in the singular point analysis. So that gave us the solution of the singular point, which basically gave us a definitive value for the mass loss rate. And we could do that by only specifying the mass, the luminosity, and the photospheric radius of the star. The key thing was that our theory, for the very first time, had no adjustable parameters. We found that the terminal velocity of the wind is always somewhat larger than the escape velocity, and in fact, these winds should blow between 1 and a few thousand kilometers a second, which was well in line with observations, and the rate of the mass loss was large. We found that it was several times 10 to the minus 6 solar masses per year. Now, this has major consequences because this means that the star would lose up to about 33% of its mass during the main sequence hydrogen burning phase. And that meant that there's a possibility that in some of these stars, nuclear process material deep within the bowels of the stars could actually be exposed at the surface, having dramatic impact on stellar evolutionary theory. Subsequently, John and I tested the theory in depth against observations by actually doing the non-LT simulations for the statistical equilibrium of both helium and hydrogen lines as a function of the radius, which we now had in the stellar wind in the CAK theory. We can now make definitive predictions on the non-LT emission line profiles and the strengths, and that analysis then provided us with strong confirmation of the theory of OF stars. Now, before I arrived in Boulder, in 1972, John wrote a paper that I don't know that he realized it at the time, but would become a seminal paper in the field of radiation hydrodynamics. This paper had a great influence on me and my subsequent career, as well as Dmitry Mihalis, who I then began to do work with. Now, what did John do? Well, John started with the general relativistic formulation of Lindquist, who had developed a formalism for basically doing radiative transfer in a covariant way. But John carried this into the co-moving frame of the fluid. And as a result, he was able to derive all the important velocity-dependent terms in the transfer of radiation in the co-moving frame, okay, and got the first true equation of radiative transfer, including the relevant velocity-dependent terms. This had not been done before in an expanding atmosphere. Now, John's approach at that time and his interests were to basically apply this to nonlinear pulsation in pulsating stars like our Lyrae. But in fact, this equation, which became the basis of the work that Mihalis did 10 years later in developing the famous book, Foundations of Radiation Hydrodynamics, John had developed it and then showed for the first time through a beautiful scaling analysis what the important terms were in each of the different regimes, and I'll discuss that in my own work following this. So we developed the first combined moment equation, where here's an Eddington factor, it can be an Eddington tensor, which lends itself to a solution through an Eddington tensor or variable Eddington factor approach. Okay, now, We've talked about our foundational work in how hot star can drive winds, but where do these hot stars come from? Where do the O stars come from? So years later, I devoted my attention to the field of star formation. And then the key question in the field at that time was, how do you get massive stars? Okay, so this is a major theoretical challenge. So the formation mechanism, well, is it gravitational collapse of an unstable cloud? Is it competitive Bundy-Hoyle accretion? Can you get this by coalescing molecular clouds together? And how can you gravitationally have these collapsing clouds overcome the so-called Eddington barrier, preventing further accretion to occur? What determines the upper mass limit for stars that are seen up to masses of at least 150 solar masses, and in recent cases up to 300 solar masses? And more importantly, how do the feedback mechanisms such as outflows and the radiation affect the subsequent evolution of protostellar evolution? These mechanisms, I should point out, also have major effect on the formation of clusters. So you can ask the question, how did these stellar clusters in which massive stars are present form themselves? So the key question that one must actually solve is taking into account the strong effects of radiation pressure. So let's examine that for a moment. If you have massive stars on the order of about 20 solar masses or above, then the Kelvin time is less than the formation time. And this has major consequences because this means that the nuclear burning occurs during the accretion phase before the star even makes it on, protostar makes it onto the main sequence. So what does this mean? It means that there's a radiation of enormous amounts of energy. So in fact, if you take a star in the order of about 100 solar masses, 100 times that of the sun, its luminosity is essentially the same as the Eddington luminosity if the major source of opacity were electron scattering. But in fact, in most astrophysical flows, that's not the case at all. It's the dust that actually dominates and can dominate the electron scattering by a lot. So this means that the force of radiation can begin to oppose the downward force of gravity for stars as small as 10 solar masses. You can show this on the back of an envelope. Well, we know that observations give us massive stars on the order of 100 solar masses or more. So this presents us with a really heavy fundamental problem. How do you sustain a sufficiently high mass accretion rate onto the core of a star to push it past the Eddington barrier? And does this radiation pressure give you a natural limit to the formation of high mass stars? In order to approach this problem, I developed with my colleague Chris McKee and our postdocs and graduate students at Berkeley the fundamental approach to gravitational radiation magnetohydrodynamics. The code we developed, Orion, has become a state-of-the-art code in the world for star formation. And without going into the details of this, I would just point out that in order to solve this problem, you're dealing with a highly nonlinear coupled set of elliptic, parabolic, hyperbolic equations that all have to be solved simultaneously and to get the dynamic range on an adaptive mesh. So we developed this by actually redoing the type of scaling study that John first showed back in 1972, and how you retain the most important velocity-dependent terms in this flow. Now, Dimitri and I wrote a paper 10 years after John in which we carried John's work not in the co-moving frame, but into the mixed frame. And that had major advantages for the field of star formation. So we had to redo John's analysis and what the important terms were in the mixed frame, and they're somewhat different. We developed our system of equations that are exact to order V over C in the static diffusion regime and correct to leading order both in the dynamic diffusion regime and in the optically thin regime. Okay, now let's start with the first ideal simulation. Picture on the left will show a face-on view. This will show a side-on view through the three-dimensional box. And basically, we're starting with cores that are the embryos of where stars form. They're typically on the scale of about 1 to a few hundred solar masses and have size scales of about 1/10 to a few tenths of a parsec. The dynamic range in our first simulations were 8,000. You could only achieve that with adaptive mesh refinement. After a while, the central object begins to have a very large radiation pressure effect on the surrounding gas that's trying to build onto the star. But in fact, the radiation pressure, here's the Eddington barrier staring you right in the face, will blow these radiation-driven bubbles and not allow matter to append onto the disk and then onto the star. So this starts to give you the natural limit, and you have to get past that. Well, you notice that the basic bubbles form asymmetrically, and they form with perturbations on the surface. So this is key. After a while, the perturbations increase, the bubbles become even more asymmetric, and then finally, you are led to an analog of the hydrodynamic Rayleigh-Taylor instability, because these bubbles will then become Rayleigh-Taylor unstable, but driven by radiation forces, not by gravity. We published our first paper on this in Science in 2009, and you can see here as the bubbles collapse, matter can now move onto the disk and then in spiral into the star. The star can't even be seen here because we have many, many orders of magnitude of spatial dynamic range here with adaptive mesh refinement. This essentially solved the decades-old problem of how you form massive stars. And finally, the bubbles collapse completely, and you can form massive stars of 10, 20, 30, 40, 50, up to 100 solar masses and above. Now, these, if you look at the observations tell us that in the galaxy, where massive stars are rather rare, they tend to form mostly in massive binaries. So how do you get a massive binary? So the next thing I'm going to show you is a movie that, if you look at the top, that is on the global scale, then you zoom all the way in with adaptive mesh refinement. So this is the evolution of forming the disk. Then you start to build the radiation-driven bubbles. They go radiation-driven unstable, Rayleigh-Taylor unstable, and you in fact now start to form one, but interestingly enough, a binary, and a low mass object of about 1/10 of a solar mass. The key to forming the binary is a gravitational instability in the disk itself. It turns out to be the sling instability. And so we were able to show, in this instance, that you can form a massive binary with about 30 solar masses and its twin of about 18. And that solves the problem of how you actually get massive binaries. Now, let me actually skip that slide. OK, now, the next important thing is how does feedback from the stars that are forming, massive stars, affect the environs? Okay, so in this movie, we will actually see, this is on the large scale, and this is the collapse of a turbulent core. The turbulence is developing strongly here. And if we go to the right, we zoom all the way into the center, and we're going to actually form mainly a single mass star, high mass star. What does the radiation do? The radiation from the forming protostar heats its environs around it, thereby raising the so-called Jeans mass. And that means that preferentially you suppress low mass star formation, and you in fact put most of your energy into a massive star. So when you take into account the radiative effects, you get preferentially massive stars. Okay, now I want to move on to the large scales. So to begin with, we're going to look at star formation across very large dynamic ranges with full multiphysics feedback. Here, we're going to do the simulations with a multi-staged approach where all the relevant physics will enter throughout the evolution. Okay, our code Orion it's an adaptive mesh refinement radiation magnetohydrodynamic code, of course in 3D. It has sync particles, outflows, chemistry, now variable Eddington tensor radiative transfer, and photoionization. We evolve these large-scale clouds on a dynamical time scale of the entire cloud, and then perform zoom-in calculations to bring in the full effects of the feedback physics. I'm going to discuss this in 2 stages. The first stage is something on the order of a mini giant molecular cloud, roughly 5 to maybe 10 or 15 parsecs in scale. And then I'm going to take you to our latest simulations, which nobody in the world is actually doing yet, to evolve all the way from the galactic disk at a kiloparsec all the way down to the formation of clusters. So starting with the first part. There are 3 scales here. I'm going to spend my time on the last scale. The first scale is that we evolve very large supersonically turbulent magnetized simulations and develop very dense filaments. These filaments have now been observed, and they are what observers identify as infrared dark clouds. Okay, a key advantage of using these simulations as the starting point is that in the zoom-in simulations is that the cloud already has gone through the full magnetohydrodynamic turbulent cascade phase from the large scale all the way through gravitational collapse. And so we're now beginning with much more realistic conditions, initial conditions, and therefore low mass and massive star formation will now have much more realistic initial conditions. Now, we then pass through a clump scale, which is a few parsecs. We've written some papers on this. I won't discuss it today. Now let's go down all the way to the core star scale. Here, the zoom-in simulations will have the full coupled feedback physics coming in. We select regions to concentrate on and examine the formation of clusters deep within those regions. Okay, this then enables us to start to compare in detail with the actual observed initial mass distribution or mass function, the IMF in the galaxy, which is the probability that stars have the mass that they get, protostellar mass function, the protostellar luminosity function, outflow observations, and finally multiplicity. So let's actually look at a scenario of what you're going to see today. We start with, after 350,000 years, we develop these dense filaments that are now being observed by the observational community. Stars then form over the next 350,000 years, and they light up and illuminate their environs surrounding where they form in these clusters. We can go deep into this and for the first time examine the magnetic field structure that is appending right onto the formation of the deep filaments, or we can go to the outer scales and look at the global morphology of these field lines on large scales. We can go further in, all the way in. You can't see it because the scales are many tens of thousands with AMR, and look at individual properties such as outflows. These are 3 individual stars taken from here, and look at the protostellar binaries in a zoom-in cluster region. Now, observations, this is a beautiful observation, show you what the observers can see now. They find massive, long and dense filamentary clouds. They have magnetic field structures that are perpendicular to the clouds, very, very close to what we're actually predicting with the simulations. So now we can begin to look at the dynamics of the field over 350,000 years, if this will play. And for the first time, and of course observers can't get this kind of resolution, the stars are beginning to form. The field lines have a lot of dynamics. They are channeling mass coming in from outer regions, strongly channeling it onto the filaments, and we can now begin to study that channeling and how the stars build mass in a cluster. This is after now 700,000 years of evolution, and we're seeing the cluster form, and you can start to study now the dynamics of how mass gets onto that cluster. Okay. But these filaments are not simple. They're fibers. And in fact, they have a fiber-like substructure. This is a detailed 3D rendering of what these things actually look at. Of course, the observers can't see this type of resolution. The zoom-in simulations allow us to study the hierarchical structure in these fiber-like filaments that lead to star formation. So here are some observations, a beautiful region called B112, 212 in our galaxy. And it is shown that the fibers actually break up and fragment into chains of cores. This is observational. We see exactly this in the 3D simulations. This is a projection in 3D. These are our simulations. You can see the cores developing along the line of the filaments, and it's a chain of cores caused by fragmentation of the filaments themselves. Now, the cores are actually the embryos of where the stars form. So you can have 1 to a few stars forming in a core. Here we're actually going further in, and we're showing the, I'm blowing up that region now. You can see the stars actually forming within the cores along the filament. And at the juncture of 2 colliding filaments here, we get, out of a total of about 80 or so protostars in the cluster, we get a strong number of stars forming in that dense intersection region, showing that star formation is enhanced in these colliding flows because these turbulent filaments and fibers will actually collide with each other. So now let's actually take a look at this over 350,000 years of evolution. There we go. Okay, so we start at 350,000 years with the development of the IRDCs that observers are now seeing. And now we evolve for the next few 100,000 years as stars actually start to form singly and in small subclusters along the filament fiber structure. These objects, I'm showing you the luminosity now, of these stars are starting to be born as protostars. They irradiate their surrounding environs and have input into the environs with both radiation and protostellar output feedback, giving both radiative heating in the regions close to their formation, and also they deliver momentum to those environments. And the gas is heated to up to 100 Kelvin, which is 10 times the ambient undisturbed initial temperature. So we now can swing around at 700,000 years to see what the structure of this actually looks like. Okay, now we can begin to look at the individual properties of the cluster to compare with observations. In the upper left, I'm plotting the mass of stars as a function of time for each of the 82 stars in the cluster that we form. We see that many of the stars have already reached their final mass. Some are still accreting. We go to the picture on the right, concentrating on the dashed line. We see that basically, this is the median mass of a star in our cluster. It fluctuates around 0.2 solar masses. Well, this was a great thing to see, because now you can show that this is exactly consistent with the observed initial mass function in the initial mass function in the galaxy, which is also 0.2 solar masses. And we see down at the lower part here that the mass accretion rate as a function of time traverses between about 10 to the minus 5 and 10 to the minus 7 solar masses in agreement with observations. Okay, quickly go through this and then I'll get to the largest scales because I'm pushed for time. Here we're looking at star formation efficiency and star formation rate in the clusters. On the left, the number of stars that are formed in the cluster as a function of time is a beautiful power law with a power law index of about, exponential index of about 1.5 that says that the star formation is accelerating. In fact, if you look at the star formation efficiency in our cluster, it goes as quadratic in time. This means that the stars are basically gaining their mass quadratic in time, but their star formation rate drops down by 1 power, and it goes as a function of time, so the star formation is accelerating. Okay, that is now seen in observations. The star formation rate is found to be accelerating both for the driven turbulent simulations I'm showing you today, as well as undriven turbulent simulations where the turbulence can decay and cannot stop the star formation process. But decaying turbulence gives you a star formation efficiency that goes much more rapidly. It goes as time cubed with a star formation rate going quadratically. So what does this mean? This means that driven turbulence that comes in at the large scales in the galaxy significantly reduces star formation efficiency. Finally, if you want to compare the star formation rate across galaxies in the universe, you look at the dimensionless star formation rate per freefall time, and we get between about 0.03 and 0.04 with an efficiency of about 4%. If you look at observations, starting with our own Milky Way galaxy, going out to higher redshift galaxies, much earlier time in the universe, the observations show you get that efficiency at about 0.015, but if you go into the Milky Way, several of the clouds that are producing stars have larger factors by a few, so the simulations are well within the range. Okay, now lastly, well, 2 more here, and then I'll go into large scales. This is a complicated plot. I just want you to concentrate. This is the initial mass function, the probability that you form stars at a particular mass in our galaxy. Okay, the open boxes are our simulations, and the solid blue line here are the observations, the so-called Chabrier initial mass function. Okay, we find that our median at the end of our simulation agrees almost identically with what the observations show, that the typical star that forms in our galaxy is 0.2 of a solar mass. We find that 2 of the 5 theoretical models we compared with and the Chabrier IMF are well fit by the observations. I'll just briefly mention here, without going into detail, We have calculated the luminosity of our cluster as a function of time, and that agrees remarkably well with the latest surveys of several hundred sources and clusters, where we get mean luminosities of our cluster of about 5 times solar luminosity, and the median 2.1, and the observations show that basically it's about 5.5 and 1.8, so fantastic agreement on that. Now outflows.
I'd like you to end with this.
Okay, let me just get to the last slide.
Yes.
Okay. On the last slide, actually, I'm going to show the last of a series here in 1 second. We've now begun the simulations all the way at the scale of the galaxy, and for the first time bringing this in by several orders of magnitude. And I won't go through how we do that, but we use zoom-in techniques to basically go from the scale of a kiloparsec, now for the first time, down to resolution of 25 AU, and AU is the distance from here to the sun. That's a dynamic range of 10 million, or 23 levels of adaptive mesh refinement with full radiation magnetohydrodynamics, and we're starting to form the first stars in that cluster all the way down, and it will take several more months of computation to get the cluster out. So I will end with that. I'll leave my summary on here. And I'd like to leave you with the final words. John and I continued our collaboration for many years past stellar winds. In fact, we wrote several papers together in 4 major areas for the next 20 to 25 years. We worked on Compton-heated winds. We worked on X-ray heated coronae from accretion disks surrounding black holes. We wrote a series of papers that included Peter Dykema on non-LTE, in which we developed new techniques to approach the non-LTE problem, most notably bringing in for the first time adaptive frequency in the non-LTE simulation, and also low-mass X-ray binaries. So I want to say to John personally, we began a great friendship many years ago in Boulder. That friendship has continued. We've had a fantastic run. It's been a privilege to work with you all these years, and I hope we continue to see more of your presence. Thank you. There's some time for a couple of questions, maybe.
Sure. Okay, well, I think we have time for one question. And do we have someone who would like to ask a question? Please raise your hand. Lauren. Okay.
Well, this is probably a really dumb question because I don't know anything about astrophysics, but as a non-astrophysicist, I've heard about dark matter. Now, how does that, if you're looking at these large-scale things, if you don't know where that stuff is, how can you do this? Do you make the assumption that it's just isotropic?
So basically, we don't take dark matter into account because that exists on much larger scales than even the galaxy. But we start basically with the physics we understand at the largest scales in the galaxy, and then attempt to bring that all the way, which we believe that is correct physics, without knowing how dark matter influenced galaxy clusters, et cetera, but gives you the galaxy, and then bring that down to the formation of individual stars, as I'm showing you here today. So we don't need to consider dark matter for these simulations.
Okay. Thank you very much, Richard. If you have more questions, we have a break coming up.